Hello, Electromagnetism, where we will look at the problems in electric field and capacitors. So let's first look at the first problem. So the statement of the problem is we have a point charge Q is placed at a corner of a cube of side A as shown below. So here is a cube which has a side A, and the question is what is the electric flux through surface ABCD. So this is ABCD. So we want to find out what is the flux through this surface. So let's first write down the expression for the electric field due to charge Q. So this is the electric field vector, and this is the magnitude of the electric field vector, which is Q over 4 pi epsilon naught, and r cap is the unit vector which points radially outwards. So this gives us the electric field vector due to this charge Q. Now next part that we want to do is we want to write the area vector. So A bar is the area vector, and the way we write this area vector is E square times n cap, where A square is the area and n cap is the unit vector which is pointing upwards in this direction. So now we want to find out the flux through this surface ABCD. So what we do is we take the dot product of electric field vector and the area vector. So this is the electric field vector that we have, Q over 4 pi epsilon naught r cap, and we take dot product of this with E square n cap. So essentially what we get is the dot product between r cap and n cap, but these are the unit vectors. Now let's find out the angle between these two unit vectors. So since this is charge Q, r cap is pointing radially, so it is lying on this surface, while n cap is pointing upwards. So the angle between them is 90 degrees, and since we are taking dot product, the dot product is 0, so the flux through the surface is 0. Let us look at the next problem. The electric field lines on the left have twice the separation of those on the right hand side as shown in figure. If magnitude at point A is 40 volt per meter, what is the force in Newton on 20 microcoulomb charge placed at point B? So here is the charge which is placed at point B, and we have been told that electric field lines on the left have twice the separation of those on the right hand side. So these are twicely separated than the separation between those two, and the magnitude of this electric field at point A is 40 volt meter. So double separation of the field lines at point B with respect to implies that the reduction of electric field by a factor of 2. So what it implies that the electric field at point B, you can straight away see that it is 20 volt per meter. And since we know now the electric field at point B, we can calculate the magnitude of force at point B, which is F is the magnitude of the force is charge times the electric field. So we get 20 microcoulomb, so we have this 10 raised to minus 6 factor over here multiplied by the electric field. So if you calculate, then we get the magnitude of the force as 4 into 10 raised to minus 4 Newton. Look at the next problem. An infinitely long thin wire of uniform charge density of 1/4 into 10 raised to minus 2 Newton per meter is there, and what is the magnitude of electric field at a distance of 20 centimeter from the axis of the wire. So we have this magnitude of the electric field vector due to infinite charge wire at a distance r is given by, so this E is the magnitude, lambda is the linear charge density. So what is the charge per unit length? That is what is lambda is. Then this is divided by 2 pi epsilon r. R is the distance. Now straight away calculate this. We just have this lambda as 17 98 into 10 to the 9 Newton meter square per coulomb square into 0.25 into 10 to the minus 4. Actually, this number is 1 over 2 pi epsilon naught. Okay, that is what this number is. This lambda is 0.25 into 10 to the minus 4 Newton per coulomb, and this is what the 1 over r term is. So if you do this calculation, then we get this electric field, magnitude of the electric field as 2.25 into 10 to the 8 Newton per coulomb. Look at the next problem. We have the difference between equivalent capacitances of two identical capacitors connected to in parallel to that in series is 6 microfarad. So what is the value of capacitance of each of the capacitors? So the effective capacitance when the capacitors are in series, let's call this as CS. So 1 over CS is 1 over C plus 1 over C. That's how we write the effective capacitance. So we get this CS as half of this C. Now for parallel effective capacitance, we just add the capacitance, so it's twice C. Now we have been told that the difference between these two is 6 microfarad. So we just now plug in the expressions. So the effective capacitance for parallel is twice C, for series is C by 2. So if you solve this for C, we get the capacitance as 4 microfarad. Next problem, the following figure shows 3 points A, B and C in uniform electric field E bar. The line AB is perpendicular and BC is parallel to the field lines. Which of the following holds good? Where VA, VB and VC represents the electric potential at point A, B and C respectively. So we have been given different options and we are asked to see which one of them is correct. So this is diagram that we have. So let's try to analyze this. So the electric field lines lie along line EB are equidistant. So if you see this, the electric field lines are equidistant, which implies that the electric field is same at point A and point B, and that's the convention. So if you have equidistant electric field lines, it will imply that the electric field is same at those 2 points. Now the convention in which we draw these electric field lines is the arrow indicates the decreasing strength of the electric field. So you can see that the strength of the electric field is decreasing as we move from point B to point C. Okay. So which implies that the electric field potential at C is less than that of the electric field potential at point B. So from this we can conclude that this statement where the electric field potential at A and B is same while the electric potential at point C is less than the potential at point B. Let's look at the next problem. A hot filament liberates an electron with zero kinetic energy. The anode potential is 1200 volts. The speed of electron when it strikes the anode is, so we have to calculate the speed of the electron. So let's go to the conservation of energy equation where we have the initial energy of this electron equal to the final energy. So essentially the electron has initial okay, so before we go ahead, let's look at the difference between the kinetic energies. So this is the change in the kinetic energy is equal to the change in the potential energy. So since initial speed of the electron is 0, the initial kinetic energy is 0. So that's how we get 1/2 mvf square is equal to q times the potential. So solve this for the speed. So we get the speed of the electron as square root of 2 times the charge of electron, the potential through which the electron has been accelerated, and over the mass of the electron. So if we plug in the numbers, then we get the speed of electron as 2.1 into 10⁻⁷ meter